Hello, so welcome to part 6 of the differential amplifiers. Okay, so in the last video we looked at the common mode changes. So assuming V1 and V2 changed, what would happen? And in this video we are going to look at the input and output characteristics of the differential amplifier. So we know for sure that if the differential input, so V in 1 minus V in 2, is 0, then the differential output would also be 0. So we just say the differential output is 0 when the differential input is 0. Okay, so we looked at that in the previous video. Now we are just going to study the input-output characteristics, and that will make us appreciate what we are doing better. Okay, so for now, I have V in minus V, so V in 1 minus V in 2. And I'm going to start off with the current. So we have IC1 and IC2. At a point where the differential input is 0, that means V in 1 and V in 2 are the same, so their difference is 0. We know if I sketch the differential pair here, of course with a tail current source, VCC. Okay, so when V in 1 and V in 2 are the same, what happens to the current? The current will split IEE. So this half you have IEE over 2, and this half you have IEE over 2. Let's not forget IC is approximately IE. IE here is emitter current and IE is a tail current source value. Okay, so I can put a mark here and say both of them have a value of IEE over 2. Okay, but what if V in is far bigger than V2? So we saw when we put V in 2 volts and V in 1 volt, it got to a point that the difference between them meant that so if I have 2 volts and we are assuming 0.7 between the base and the emitter, then the voltage at the emitter or the tail would have to be 1.3, keeping this device not in forward active mode or even off, because the base emitter voltage is not forward biased, so no current would flow. But the difference should be significantly high. Assuming we had 2 volts here and 1.9 here, then we do the same analysis. This time around the base emitter voltage will be 0.6, which means that one condition that should always hold is IC1 plus IC2 should be equal to IEE. So in this case, the circuit is not going to be symmetrical. There will be more current here compared to the current here, but this will not completely go off. So that's what we want to analyze using the output-input characteristics and see that clearly. But we do know that if the difference between the V in and the V out, what I call differential input, is high enough, then all the current will flow through IC1. So if the difference is high enough, then this value would have to be positive enough. So somewhere here, IC1 will be equal to IEE. So then this value has to be IEE. Okay. And during that time, IC2 has to be 0. So this is a curve for IC2. Let me change. So IC2 would have to be 0. Okay. Now when the reverse happens and V2, that's the input voltage at the transistor 2, is also way higher than the input voltage at transistor 1, then similar thing would happen. The current would rather go through this side, and the same analysis, we have 2 volts, base emitter voltage is expected to be something around 0.7. Here becomes 1.3, and we have 1 volt here, meaning that this device is not forward biased and no current can flow through here. So IC will take all of the tail current, IEE. So when the differential input is negative enough, meaning the V into is far bigger than VA1, then we have a similar scenario happening here with IC2 being equal to IEE. Okay, and during that time, IC1 should be also be equal to 0. Okay, so I have 5 points that I can plot. So I know from here it goes like that up to infinity, and this one too goes like this up to infinity. But in the middle, when the differential input is 0, so I would just try and join them. I don't know whether they join linearly, so this is just an assumption, but it's a good assumption. Similarly, we would also have this way. Okay, so this is the differential input against the 2 currents, collector currents. Now what if we wanted to plot the differential input against the single stage output, Vx and Vy? Okay, so by this I mean Vx, so let me call Vx here, and let me call Vy as the output here, so Vy. Okay. So similarly, we could derive the relationship between Vn1, Vn2 versus Vx and Vy. Okay, so when the differential input is 0, what is the value of, okay, let me just redraw the bipolar pair. So RC. So when the differential input is 0, then we expect the collector current here to be IEE over 2. Collector current here to be IEE over 2. So what will be the output voltage here? It's going to be VCC minus IEE over 2. And similarly, I'm going to have the same VCC is equal to output voltage at Vx and this Vy, IEE over 2. So when the differential input is 0, then it means that the tail current is not steered towards one direction, and they are sharing it equally because of symmetry in the circuit. Okay, so in the first instance, just as we did for the current, we find the value of the voltage here, and that's going to be VCC minus IEE over 2 RC. So I left out the RC here. Okay, now another instance is, what if the Vin is very big, more positive than the Vin2? So just as we did before, we put 2 volts at the Vin1, and 1 volt at the Vin2. So in this case, we say that the differential input is more positive. So what happens is that IC2 goes to 0. And if IC2 goes to 0, it means there is no current in this branch. If there is no current in this branch, then the voltage at this node becomes equal to VCC. So I can say that the voltage Vy becomes equal to VCC. Okay, so that should be on top. That will be higher. So Vy is equal to, so this is a value VCC. So assuming our VCC had been 5 volts, up here would have been 5 volts. Okay, now let's not forget Vy corresponds to Vin2, just not to get confused. Okay, what about another instance when okay, so what happens is that, what happens to Vx is going to be less, not up to 0, but less. So Vx during the same time is going to have a value of VCC minus the whole of IEE RC. So we know that when we interchange and this time make the voltage on the second transistor Q2 higher, or 2 volts, and the voltage here 1 volt, what we are going to get will be similar. So I'm just going to repeat these values here. I just change them. So this time I'll get Vx being equal to VCC, because the current in this branch is going to be 0, and Vy would be equal to VCC minus IEE RC. Okay, so we can join them up. And have a nice curve here. Okay. All right. So we have the differential input and the currents, and here we have the individual output current at the single-ended voltages against the differential input. So finally, what we really wanted was a curve that would describe the differential input Vin1 minus Vin2 against the differential output, that's Vx minus Vy. So all that we are going to do is we are going to take this value Vx and subtract Vy from it. The easiest one to do would be this, because at this point Vx and Vy are the same. So the output differential. Now this is called differential output, just that we get familiar with that. So differential output now becomes 0 when the differential input is 0, and that's something that we have seen before. So this is the characteristic that explains how the differential amplifier behaves. So it tells us that when the differential input is 0, the differential output is also 0. Okay, but what if the differential input is positive enough? What happens to the differential output? So you are going to get a value here, Vx. Then we take or subtract Vy from it, and that should be a negative value. Remember, Vy was Vcc. So if I take Vx minus Vy, then I'm going to get negative of that. So we have that voltage somewhere negative. So here, when the Vin is positive enough, at some point, the output voltage is going to be negative RCIEE. Okay, what if this time the Vin2, and it doesn't really matter which one is Vin2 or which one is Vin1, it's just about the difference. So you could match Vin1 to X or match Vin2 to Y. So you could just do Vin2 minus Vin1. Right here you'd have to do Vy minus Vx, and the result should be the same. Okay, so when you come here, what's the difference going to be? We are plotting Vx against Vy as our differential output. So we have Vx being a big positive Vcc, then we take away Vy, which is going to be minus Vy, which is Vcc, minus IE RC, and this means we are going to get positive. So this value here, let's say, is positive RCIEE, and that's going to be what we are going to have. So I can just try and join them. Not really sure what happens here, that's quite gray, but from the look of things, this is what I was able to come up with. So let me summarize everything. So if I take the differential output against the differential input of a differential amplifier, then the input output characteristics looks something like this. Now what this means is that within a particular window there is voltage gain. If the voltage increases here, the differential voltage increases here, there will be a particular gain, but after this window, any increase in the differential input gives me no gain, because in a single stage amplifier, if you recall, if I had voltage input against voltage output and I plotted V out against V in, I would have got something like this, showing that the slope will be the voltage gain. So the higher the slope, the bigger the gain. So if the input voltage increases to 1 volt and the slope is like this, I'm going to get an output of 1 volt times AV. And if the slope is like this and the slope is AV2, I'll get an output voltage of 1 volt times AV2. So that tells us that for the differential pair, somewhere around the origin, we have amplification. But when the difference in the input becomes too big, then we no longer have amplification. So we look into this into details. Until then, see you. Bye.